Okay, let's now take a look at the second impurity function that we can use. Basically, we've seen that the worst distribution that can happen is that you have in your last leaf all classes equally represented. Yeah. So in this case here, you have a leaf, your last leaf, and you have, for example, 3 crosses and 3 circles. Yeah. So here k equals to 2. Yeah. So if k equals to 2, all classes have a probability of 1 over 2. It's 50%. Yeah. And this is what actually is written here. So this is something we want to avoid at all costs. Yeah. So here you see that all the distributions are 1 over k. When k is 2, it's a probability of 50%. And now we're gonna actually calculate or make sure that the difference between our two distributions is as high as possible. And therefore we're gonna use some math, and it's called the Kullback-Leibler divergence. If you're interested in the background and how it relates to entropy and cross entropy, please take a look at the optional session that I give just after this one. Yeah? Is it important? Well, in some way, yes, because we will be using cross entropy mainly as a cost function for classification algorithms. Yeah. Okay, so let's take a look at the KL divergence. Yeah. So it tells you how different two distributions are. Yeah? And in our case, we want the distribution to be as far away as possible from the scenario where you have equal probabilities. The formula, so it's written as KL, but often it's also called DKL. This is your two distributions you want to compare. Distribution D is the one we do not want, and the value is 1 over k, as we've seen here. Yeah? So we sum over k of distribution Q and then the log of Q over D. Yeah? Remember, the log of A divided by B is the same as log A minus log B. So what we're going to do is we're going to rewrite this equation as the sum over k, qk, times log of qk, and this is the first term, plus, or sorry, it's minus, because it's a division, minus the sum over k over qk times the log over dk. And we know that dk is 1 over k. Yeah? So this term is going to change 1 over k. So the log of 1 over k is minus the log over k, and the minus of this one and minus the log over k becomes a plus. So it's sum over k, qk, and then we have the log of k. Yeah. Now the log of k is a constant. Yeah. So we can put this in front of the summation. Yeah. So we have then in this case log of k, and then the summation over k over qk. Yeah. But if we're gonna sum over all classes, we have the 1. Yeah. So this is equal to 1. Yeah, that's how a distribution is defined. The sum over all classes, like here, if you take the sum over all classes, you're gonna have 1. Yeah, because it's 50% plus 50% is 1. So that means that we have a constant here. This is also a constant, and we can actually drop this. If we minimize or maximize a function, the constant will not have any influence. So we actually want to maximize over qk, yeah, the sum over k, qk times times log of qk. This is what we want to maximize, but this is the same as to minimize over qk, yeah, minus the sum over k, qk times log of qk. Yeah, and this is actually the minimization problem that we need.